You are looking at one of the most important objects in the modern world. It is thinner than a human hair. It has no computer chip, no battery, no processor, and no moving mechanical parts. But every second, trillions of signals travel through this tiny strand, carrying phone calls, videos, financial transactions, artificial intelligence, data, and almost the entire global internet. Can you guess what allows information to cross oceans and continents at nearly the speed of light? This is an optical fiber, a tiny strand of engineered glass that became the foundation of our digital civilization. But the incredible part is, this technology begins from one of the most common materials on Earth: sand. Inside ordinary sand is silicon dioxide, also known as silica, the same basic ingredient used to make glass. But the glass inside an optical fiber is completely different from the glass around us. A normal window blocks too much light after only a short distance. An optical fiber must allow light to travel for tens or even hundreds of kilometers while losing only a tiny fraction of its energy. To achieve this, engineers need to create some of the purest glass ever manufactured. The process does not simply involve melting sand into glass. The material must be rebuilt with extreme control. Silica is purified into special chemical compounds. Inside advanced manufacturing systems, these materials react under carefully controlled conditions. Layer by layer, ultra-pure glass begins to form. Every impurity must be removed, because even microscopic contamination can scatter light and weaken the signal traveling inside the fiber. This level of precision is what separates ordinary glass from optical communication technology. The result of this process is called an optical fiber preform. At first, it looks like a large transparent glass cylinder, but hidden inside this object is the complete design of a future optical fiber. The center region will become the core. The outer region will become the cladding. Even though the final fiber will become incredibly small, the relationship between these layers is already created inside this large glass rod. The entire structure will later be reduced thousands of times. The reason this structure works comes from a powerful principle of physics: total internal reflection. When light enters the fiber core, it does not escape through the sides. The difference between the core and cladding forces the light to remain trapped inside. Instead of electricity moving through metal wires, fiber optics use controlled pulses of light moving through glass. These pulses represent the digital information that connects computers, phones, and data centers around the planet. Now, the massive glass preform must become a fiber thinner than a human hair. To do this, it enters the fiber drawing tower, one of the most precise manufacturing systems in modern engineering. The preform is positioned vertically above a specialized furnace. The lower end is heated to temperatures close to 2000 degrees Celsius. At this temperature, the solid glass does not melt like water. It becomes soft enough to be carefully stretched. Gravity and precision machines begin pulling the softened glass downward. A large glass cylinder slowly transforms into an extremely thin continuous strand. The process must remain perfectly stable. The pulling speed, temperature, and tension all have to be controlled at the same time. A single preform can create kilometers of optical fiber while maintaining almost identical microscopic dimensions from beginning to end. As the new fiber moves through the tower, other system is constantly watching it. Laser measurement equipment scans the fiber thousands of times. The target diameter is around 125 micrometers, only slightly thicker than a human hair. Even tiny changes in size can affect how light travels inside. The manufacturing system automatically adjusts the process to keep the fiber within extremely strict limits. But this perfect glass strand has a problem. It is extremely fragile, so immediately after drawing, protective layers must be added. The fiber passes through coating machines that surround it with special polymers. These coatings protect the glass from scratches, moisture, bending, and physical damage. Inside, the microscopic core remains clear enough to guide light across enormous distances. A real internet cable is not made from just one optical fiber. Modern cables can contain hundreds or even thousands of individual fibers. Manufacturing machines organize these fibers into precise bundles. Additional materials are added around them. Strength fibers protect against pulling forces. Water blocking systems protect against moisture, and a strong outer jacket allows the cable to survive harsh environments. Before these cables are installed, they go through extreme testing. Engineers send controlled laser signals through long sections of fiber. Special instruments measure how much light reaches the other end. The amount of signal loss must be incredibly small, because a tiny defect inside the glass could affect communication across huge distances. Only fibers that pass these tests become part of the global network. Finally, these strands of glass leave the factory. They are installed below cities, across countries, and even across the ocean floor inside massive submarine cables. They connect data centers, servers, and billions of devices. Every video you watch, every message you send, and every artificial intelligence request you make may travel through one of these tiny pathways of light. Something that started as simple material from the Earth was transformed through chemistry, physics, and extreme engineering precision into one of the most important technologies humans have ever created. A strand of glass smaller than a human hair now carries the information of our entire digital world, the invisible nervous system of the modern age.